This is the sound of two black holes colliding and merging. Where did this sound come from? A long time ago, in the distant reaches of the universe, two black holes, each about 30 times as massive as our Sun, were locked in orbit and spiraling in towards each other. The only visible traces of this spinning cataclysm would have been the way their gravitational fields warped the light of distant stars. Even as they collided and merged, there wasn't a flicker of light to be seen. The real and very violent action in this system was in the form of gravitational waves, ripples in the very fabric of space and time. These waves were constantly draining energy from the black hole orbits, leading to their ultimate collision and merger to form a single black hole. At that instant, the power of the gravitational waves was 50 times greater than that of all the stars in the universe combined. That pulse of gravitational waves, lasting only a fraction of a second, expanded through the universe, passing unimpeded through countless galaxies. About 1.3 billion years later, it reached Earth. Gravitational waves alternately stretch and squeeze space itself and everything they pass through, but the effect is minuscule. Their effect on Earth here has been vastly exaggerated to help visualize something that is otherwise invisible on this scale. To detect them and directly measure their properties, scientists built LIGO, the most sensitive measuring device ever made. LIGO uses a device known as an interferometer to measure the tiny displacements in space. In this simplified representation, a laser beam is sent towards a partially reflecting mirror and split along two paths. The beams travel along the 4-kilometer arms and reflect back towards the central mirror, which recombines them, directing their light to a detector. As the gravitational waves pass, the distance between the central beam splitter and the end mirror stretches along one arm and compresses along the other. This changes the time it takes the light to travel along the arms. The recombined light waves shift with respect to one another and produce a signal at the detector. Incredibly tiny stretching and squeezing of space can actually be measured directly in this way. How little does space distort to make this signal? Let's zoom into a hydrogen atom until we reach the proton at its core. LIGO is so sensitive it can measure changes in distance as tiny as 1,000th the diameter of a proton. And this tiny measurement, made by LIGO, was the final step in a journey that began 1.3 billion years ago in the distant universe when two black holes collided.